Howdy, howdy, this is Mr. Potter. In today's video, we're going to take the idea that we had in our previous video, taking a stack and writing it using the dynamically linked nodes, and doing the same thing to create a queue. What's going to be important here is there's going to be a slight change in what we've done before, and that's the idea of using nodes that are doubly linked. Previously, we've talked about nodes that have a data part and a next part. And the idea is that I'm going to put whatever data that I want in this data part, and next is either going to be null or it's going to point to a new node that we're going to create, that next piece of data. And then that next will point to another node. The idea behind a doubly linked node is the idea that our node will actually have not just the data part, but two directional parts. One that's going to point to whatever's next in data, and one that's going to point to whatever's previous in data. So next could point to something going on, previous could point to whatever is before. And the reason that's important for what we're talking about with a queue is that I do need to be able to not only put new stuff in at the front, but I need to be able to take old stuff off at the back. Now, this certainly can be done with one node, but you end up having a lot of traversing going on, and it tends to make things a little messy. So what we're going to do is we're going to create a doubly linked node, and the only thing that's going to be different in our struct is that I'm going to be calling it dnode, just to denote that it's a doubly shaped node. I'm going to have a type T data, and I'm going to have a dnode pointer called next and a dnode pointer called prev. And that's the only thing that's going to be different, is really this idea of having two pointers, one pointing ahead and one pointing behind. Now, the actual idea behind the queue is very similar to what we were doing before. When we were dealing with it as an array, we had to keep track of the head and the tail. And the idea is that I would be adding stuff to the end of my queue and then taking stuff off from the beginning of my queue. For our purposes, I'm going to be creating nodes, and the nodes are going to create a chain. And wherever head is, that's where I'm actually going to be putting new stuff on. So I'm going to be putting new stuff on at the head and then making sure that the links go both ways. Keep in mind that head is going to have to point somewhere, and this prev is going to have to point back. So we're going to have to make sure that we take care of all of that the way that we're expecting. So let's go to the code. So I'm going to create a new double node. So this is going to be our D node. So the whole idea is that this is going to be a struct, so template class T. This is going to be a struct dnode. And we're going to have T data. We're going to have a dnode pointer called next and a dnode pointer called prev. And that's our structure. So now we're going to implement our queue. So I'm going to create a new file, and we're going to call this linked queue.h. And so the idea here is that we're going to have very similar structure to what we had before. So we're going to define queue.h. We're going to include dnode.cpp, and we're going to template class T, and we're going to have our class Q. And we're going to have our public, and just as before, we're going to have a constructor. So here's our Q sub T constructor, and its sole purpose is to set the head to null and the tail to null. And then, of course, we're going to have bool is empty. We're going to have a void enqueue with a t data type. We're going to have a t dequeue, and we're going to have a t peak. And then we're going to have our private, and our private is just going to compose of two nodes, one dnode of type t pointer called head, and one dnode pointer of type t called tail. And then we're going to make sure that we include linkedqueue.cpp. So notice that my constructor is exactly the same format. My isEmpty, enqueue, dequeue, and peak, all of those are exactly the same. What's different is the underlying structure, how the queue is being implemented. And that means that our code is going to be a lot different as well. So let's go ahead and create our, let me save this first just to make sure. We're going to create a new file. This is going to be linkedqueue.cpp. And we're going to code up. So we're going to make sure that we include IOStream. We're going to make sure that we include std accept. And we're going to say, if not defined, q underscore h, then we're going to make sure we include linkedqueue.h. And then we can start our code here using namespace standard. And again, I've got lines 3, lines 4, and line 9 in here because we're going to be throwing exceptions if our situation is empty, if our queue is empty. So let's talk about how we know if our queue is empty. So template class T, we're going to have our queue, bool queue of type T is empty. And I know that my queue is empty if tail is equal to null. So I want to return the result of that Boolean expression. So I want to return tail equals null. Notice this looks an awful lot like what we were doing with our stack. So now we're going to have our peak. So template class T. And we're going to have our TQT : peak. And of course, if tail is equal to null, then we want to throw a standard exception out of range. Attempt to peak from empty queue. And of course, I'm saying index out of range because that really is the best error, the best exception that we can get out of that. And then once I've done that, then I'm going to return tail pointing to data. So tail arrow data. That's going to be what we're pointing at. So we're going to be pulling stuff off of our tail, and we're going to be inserting stuff at our head. So template class T, TQ, and this is going to be our DQ. And we're going to start off exactly the same. If tail is equal to null, then we're going to have to throw a standard out of range attempt to DQ from empty queue. But if we're not out of range, then we need to take care of several things. One is I'm going to have to hold on to that node to make sure that we can destroy it, so we can delete it. So I'm going to say dnode type T pointer old node is going to get tail. We're going to say that T data is going to get tail data. And then we're going to have to check something real quick. We're going to have to see if tail pointing to prev is equal to null. And if that's true, if tail previous is pointing to null, that means there's nothing else in the queue. Our queue is an empty queue. So I want to do two things. I want to set tail to null and head to null. Because if in this situation that we're talking about on line 32, if tail prev is null, that means that the data that we're dequeuing is the only data in our queue. And so we need to set our head and tail both to null. Else, we need to go ahead and just set tail to tail, tail is going to get tail prev. In other words, our tail is going to point to whatever came before in the tail. Then we need to make sure that we delete old node and we return data. So this is a little bit more complicated, but let's go ahead and talk about what's happening here. So I'm going to have a queue. Let me go ahead and just draw some nodes here. And so the idea is that I have a head, I have a prev and I have a next. Prev is the one back here, next is over here. So this is going to point to this node, this is going to point to this node, this is going to point to this node, this is going to point to this node. This is currently null, this is currently null. And I have data 3, 4, and 5 here. So here is my head, here is my tail. I'm going to check to see if tail is null. Tail is this node right here, and it's not null. It's equal to a particular node. So I'm going to go ahead and make sure that old node is pointing to this, because I want to get rid of this node after I've gotten rid of the connections. So what's going to happen now is tail.prev, that's this pointer right here, and it is not null. It's actually pointing to a node. So we're going to bypass this. Then we're just going to say that tail is going to get tail.prev. So tail is now pointing to this node. And now I can get rid of this node with impunity because I still have a well-linked thing here. The only thing I really need to take care of is I also need to take care of this stuff. The idea is that this new tail that we're talking about, its next should be null. So we're going to go down here to our code. Let's get to my pointer. So we're actually going to do two things. We're going to say tail is going to get tail.prev. And now that tail is pointing to the previous one, tail next is going to get null. And that's going to make sure that this part here is now null instead of pointing to a non-existent node. So it's just a way of taking care of everything. So we're going to get back to coding. So the last thing we need to take care of in this code is we need to take care of enqueuing. We need to take care of putting stuff into the queue. So we're going to do template class T, and we're going to tq pointer T enqueue with T data. And we're going to go ahead and create a new node. Pointer n gets new node, type T. And I'm going to set the data of this node. And then if head is equal to null, that means that this was an empty queue and we need to go ahead and make this the first node in the queue. Then we're going to do the following. We're going to say that head gets n and tail gets n. So now this is the only node that we have in our queue. Else, we need to make sure that it's put into our stream and that it links up correctly. So we're going to say n pointer next is going to get whatever head is. Head pointer prev is going to get n, and head gets n. And what we're really doing at this point is we're making sure that everything links together. So let me draw an example here. So let's say that I have an existing node. I've got a 3 here, this points to somewhere, and this points to somewhere. This is currently head. What I want to do is I want to create a new node. I'm going to put my new piece of data in here, and then make sure that this connects up. Head.next should be null at this point because it is the first element in here. So let me get rid of that. That is horrible. Let's get rid of that. So currently head next is null. So what I'm doing here is I'm saying that, not head.next, head.prev is null. Let's start this over. So I'm going to have a node here. This is my head. I've got some data in here. And the idea here is that prev is currently null because there's nothing before this in the queue. This is the leading part of my queue. This is pointing to the rest of my data. So I've got a 4 here, which is pointing back, and tail is somewhere off in the distance. But I'm creating a new node, so I'm calling this n. I'm putting a new piece of data in here. Let's call that a 2. I'm making sure that n.next is pointing to whatever head is. I'm making sure that head.prev is not null anymore. Now it's pointing to this node. And head is now no longer here. Head is now here. And that makes sure I had to do both of these links to make sure that these nodes connect to each other. A doubly linked list is a little bit more tedious than a singly linked list because I need to make sure that I've got connection going both ways. Otherwise, I could run into an issue when I start trying to do my dequeuing. So I just need to make sure that I take care of that. All right. So let's go ahead and try this out, make sure everything's good, make sure I don't have any glaring errors. So we'll go ahead and drop down to here, and we're going to compile. So g++ d linked queue.h. And again, null is not declared. This is just like what we had before. I need to make sure that if it's not defined null, then we want to define null to be 0. And remember that a null is just a 0 memory location. So we're going to go ahead and save that, make sure we save that. Now we're going to compile. Okay, and I forgot to use the capital null here. And TQ NQT, oh, that should be a void if it's just enqueuing. Okay, so this should be a void that we're enqueuing. And I need to make sure that I'm doing not null, but null. Okay, let's try compiling once more. And what's really nice, just as before, is that I can go into our queue test and just change array queue to linked queue. And then we can go through here and test that out. So we can do g++ queue test.cpp with an output of queue test.exe, and then run queue test. Ooh, error in queue test.exe, double free or correction. So 0, 6, 20, 42, 72, 2, 30, 90, 56. And notice this is the same output that we had before. The thing that's an issue is that we're now taking care of the memory on our own. And instead of having the null pointer exception that we had before, we're actually losing that data. But let's try and do that with our Morris sequences that we talked about. Again, if I change array queue to linked queue, then we'll go ahead and compile morris.cpp to morris.exe and then run Morris. Keep in mind we're entering a Morris sequence, so I can do something like 1113, and that will continue off. Notice that I have 3 1s and a 3, 3 1s and 1 3. Then I've got a 3, 2 1s, 1 3. So this Morris sequences work in the same way. The queue test gives us the issue that we had, and I can fix that by just adding one more data point here. Let me make it go up to 11. So now if I recompile queue test and run queue test, I shouldn't have, still having that issue. Okay, so the idea here behind the linked list queue is that we're using this dynamic memory allocation, and we're making sure that we take care of our memory in that way. So we don't have the fixed array, and we don't have the time crunch of having to copy the elements of an array to a new array. We've got memory that we use as we need it, that we delete as we need it. So we create new memory as we need it, or we get rid of old memory as we don't need it. So once again, this is Mr. Potter. Thank you for watching. Have a great day.